leaving group. Did you hear that term? Leaving group. So this LG, leaving group. And then what happens? The very cowardly nucleophile attacks from behind, and he kicks out who? He kicks out the leaving group, right? Because the leaving group leaves. So what do we end up with? And U hooked up to R now, plus LG. And the LG is usually negative. So this is the summary of SN2. All right. Now, I told you that when we make these Grignard and all these other alkyl lithiums, these are the ones that we use as a nucleophile because they're negative carbons, right? Negative things. So that's where that comes from. This R is not the same as this R. It could be different. It doesn't have to be the same. So an example might be if I said to you, here's propyl bromide, and I want to react this with magnesium. And what's my favorite solvent? Can I use this guy as my solvent? Acetic acid, what do you think? No good, why?
Hydrogen's connected to oxygen.
Yeah, hydrogen bonding, but more important, hydrogen is right bound to the oxygen, right? That makes it a protic solvent, right? Protic solvents are not allowed. So, maybe you want to use something like this. Can you use this? Well, all the carbons are holding hydrogens, but none of them are bound directly to H, right? The O is not bound, so you could use this. This is an ether, COC, ROR, COC. Okay? All right, what if you want to use any ether? We said that was okay, but the ether should be dry. So when you get the ether tomorrow, the stockroom person already dried it for you, so you don't have to dry it, okay? But on a day like today, if I just open the bottle and use it, I would get nothing. The Grignard would never work on a day like today or tomorrow or these days. You need to have this bone dry, okay? All right, now I use this. What am I going to make? This is Rx, right? R happens to be this part. X is the halogen. And what do we make at the end? What's the Grignard? R MgX. So at the end, I have to end up like this. So who is R? Propyl. Then I have magnesium, right? 1, 2, 3, and then I have bromide. So this is the first Grignard that you make. R has how many carbons? 3. So there should be, matter cannot be created nor destroyed, right? 3. Okay, at this point, now I have many reactions to do from here. So I have to get to this point before I go everywhere. If I can't get to here, because I chose the wrong solvent, then I'm never going to get to any of these other reactions. You understand? So that's why we cannot have any water. Water will not allow us to make the Grignard. What does water do? Water grabs an H, we make alkane. This is alkane. No more Grignard. Done. So we can't have anything protic. So that's our goal. Okay, so we're going to be using this as a nucleophile. So what if I said to you, okay, I got this Grignard, I want to react it with this, methyl iodide. We say, well, I know that this is a nucleophile because this part here is an R minus, right? That's a great nucleophile. So what does a nucleophile always do? It attacks from behind. So this part here will eventually break. carbon that's attached to the magnesium is the one that's going to attack from behind. And then this guy will go away. So the iodine will be kicked out, right? Who is the leaving group here? Right? This is going to be leaving, right? As well. So let's go back to the final product is iodine left, right? So whenever the leaving group leaves, it's I minus. Now what? R, what's the final product? If you kick out the leaving group, right? Magnesium is hanging around. This part here is propyl. 1, 2, 3. And now we have what? Attacking methyl. What have I made here? A carbon-carbon bond. Isn't that what gives me the Nobel Prize? So before I had R and I stayed R. Here I have R hooking up with methyl, which happens to be another R, right? Let's just call it a different R. And now we have 4 carbons here, right? 3 plus 1 is 4, okay? So this is your typical Grignard. What do you need? You need the alkyl halide, you need the metal, you need the dry solvent. You make RMGX first, then you react with an alkyl, anything with a leaving group. Now, how do you know what a leaving group is? Do you remember? Teacher, I think we have, no, I don't think I have 121 to any of you. All right, the leaving group is always a weak base. How do I recognize if something is a weak base? It is a weak base, but how do I know what this is? A weak base always comes from a strong acid. Okay, so we have to go back to that pKa concept. Do you remember that from 121? I have a couple of slides that I have in my content. You can take a look. You don't remember what pKa is. What is pKa, you know? You know what pH is?
Yeah.
What's pH?
Yes.
Minus the log of the hydrogen ion concentration, but really it's how acid or how basic something is, right? What's the scale? 0 to what?
14.
Good. 0 to 14. Where these guys are the most basic, and this is what? Acidic, right? And water is where? In the middle, right? 7. Alright, so we understand that from freshman half. Now, this pH, or how acid, how base something is the scale we use for strong, strong acids, or weak, weak acids, or weak, weak bases. Sorry, I shouldn't say strong, strong bases, strong, strong acids. Okay? Strong, strong acids, strong, strong bases. All right, so let's say, an analogy. So back in the day, in Gen Chem, do you know what this is funny, Rhea. This is a funny question. I drew this before, and I asked you, is this a good solvent, right? Your first name?
John.
John said, it's not a good one, don't pick that one, right? It's acetic acid, right? Because it's protein. He was correct. Acetic acid is vinegar, you know that, right? If I'm a big salad eater, so I love to put oil and vinegar on my salad. Now you say, oh, it's an acid. You're putting acid on your salad? Oh my God, are you crazy? No, that it's a weak acid. It's a weak acid, right? I don't have to worry. It's a weak acid. It's not like I'm putting hydrochloric acid on my salad, right? If I start putting HCl on my salad, then you think you call it Bellevue because I'm nuts, right? Don't want to put sulfuric acid on my salad, right? Big difference, right? Those are strong acids. Those are the heavy hitters. So when we use pH, it's only for the heavy hitters. Very strong acids, very strong bases. Nothing else. Okay. So what is the scale that we use for weak acids and weak bases? pKa and pKb. These are the scales we use for weak ones, okay? Just like if you had to weigh a mouse, would you use the same scale that you weigh an elephant on? You need a different scale, right? So we need a different scale. The strong ones versus the very weak ones. So I can put this on my salad and not think that my insides are going to be burned, because these are weak acids. Organic acids are much weaker than GenChem inorganic acids. No comparison. So that's why we need two different scales. Now in the pKa, and especially pKa, we go from 0 to 60 to something like that. You will get a pKa table when you take a quiz or a test. Whoever taught you 121 should have done the same. They have to have taught you this. I'll go over it, this is important. So all weak acids will be found on the table. Okay? Now, I said something before. All leading groups are weak bases, right? I said that. So you told me, well, a weak base comes from a strong acid, true? Give me an example of a strong acid. Well, would you say HCl, hydrochloric acid, is strong?
Yeah.
Yeah, okay. So this is a strong acid. And if it's a strong acid, if it's an acid, it's a what donor?
H plus.
H plus donor, very good. So we got this happening right away. True? What do we call this when it splits up like that? Dissociation, ionization, right? So 100% ionization. All strong acids ionize 100%. Okay, so what does that mean? You see this arrow? One way. What does that mean to you? Can I go back? Can I return this sweater? It's a clearance, last act. Macy's done. If you buy that sweater last act, clearance, what happens? You're agreeing that what? Once you buy it, it's yours. Even if it doesn't fit, you're stuck with it. One way. Cash from my pocket to Macy's. Done. As opposed to buying a sweater with no last act. You can return it, right? Okay? So here, this is one last act. Once I go from here to here, I'm done. Can't go back. All strong acids undergo 100% ionization. Now, what is this? This is the acid. What is this? This is the proton, right? So what do we call this thing? Well, this is the acid. It's related to the HCl, isn't it? So what do we, is it a base or an acid? That's Cl minus. Does it look more like a base or an acid? Well, what's a strong base that you are very familiar with? Maybe hydroxide?
Bleach.
Bleach is yeah, but it's not strong because you can use your clothes. Imagine if you put a strong acid or base in your laundry and your washing machine, what would happen? Your clothes would disintegrate, right? If you sit on sulfuric acid, you have a big hole on your fiber. It's going to eat away at the fiber. So what I'm coming back to is saying, well, you know this is negative. Does it look more like an acid or a base? It looks like a nucleophile, but is a nucleophile also look like a base or an acid? Negative things are what? Bases, yeah. Negative things are bases and positive things are usually acids, right? So this is a base. Now tell me, is it a strong base or a weak base? It comes from a strong acid.
So sweet.
So it must be a weak. And what is the name of this? This is called a conjugate base. You ever hear of these terms? Conjugate base. What does this mean, conjugate? It means we're related, like married somehow. We used to be married, right? So here, married together. Here, they got divorced. But this guy used to be hooked up to this one long ago. That's what the word conjugate means, right? So this is a conjugate base. The conjugate base of a strong acid is a weak base. That is the key you need to take, okay? So I said all leaving groups are weak bases. So therefore, now you know how to recognize. If you see something attached to a carbon that looks like the weak base from a strong acid, then it's a great leaving group because it's a weak base. Right, so come back to this. Iodine. what is the acid associated with iodide? If I have I minus, this is the base. I'm trying to figure out, is it a good leaving group or not? Well, I don't know, but this is what I do know. That if I add H to this guy, what will I end up with? HI. Is HI a strong acid or a weak acid? Of fluorine, chlorine, bromine, iodine. Do you know who's the best acid of all of them? As you go down the group, what happens? The acidity increases. So this is the best acid in group 7. So this is a very strong acid. So that makes this a weak base. Correct? And if this is a weak base, is it a good leaving group? Yep. That's why we use it. Okay? So always, when you look at something to react with the Grignard, you have to ask yourself, is this a good leaving group? Another way of saying is it a weak base? Look at this. At first I didn't understand this stuff in the beginning either, right? It makes sense of it, right? If you look at this, what is the definition of a strong base?
Yeah.
Well, an acid always gives away protons. What does a strong base do? Strong acid gives away protons. Strong base takes them in, right? Okay, so if I can accept protons easily, I'm a great base. Got that? Because a strong acid gives away protons. A strong base takes them in. So if I can take in a lot of protons, I'm a strong base. Look at this reaction. Is this guy able to take in protons? If it took a proton in, it would hook up with this one and make this, correct? Can I do that? Am I able to do it? Why not? Because this was the last exhale, right? It was a 100% reaction one way. Do I have the ability to go backwards? No, so I can never take that proton. So therefore, I am a weak base. If I can't grab onto that proton, I am a weak base. So all organic things, right away, you know, are always in equilibrium. All reactions in organic always go forward. That was why. Because they're not strong, they're weak. Weak can do anything, forward, reverse. Strong, one way. Okay, so we did our first Grignard. Okay, questions? It's a lot. Now we didn't do one thing. So I'm going to tell you, this should come in your book. This is the periodic table you're going to get on the test. Not with the colors, but pretty much the same thing. So I'm going to ask you to look over page 604, which is right next to figure 15.3 in this area here. Okay? When you get home or whatever, you have to make sense. Everything in chemistry must make sense. If it doesn't make sense, then you gotta ask. And if I can't explain it to you, then I might as well quit. Because that's not what happens after you should know how to explain anything at any time. So let's go. What did we do today? We made a Grignard. How did we do it? Mechanism. Remember I said if I want to go to California, I can go many different ways. So I said I got to California from New York. That's the starting material, New York. California is the product. But how I get there, who knows? I go through any states, you know, that or I can go straight through. Right? So the mechanism is the step by step. What happens first? What happens second? What happens etc. You know what I mean? Okay. So let's do the first mechanism. Is the easier one, the lithium. So this is how the lithium compounds are made. Okay, so what is our starting material? Rx, right? Always Rx. Why X? Why do we always start with X? X is a halogen. And what did we say about halogens? They are what? They come from strong acids when I add H, right? So therefore they make what? Great leaving groups, right? You don't have to start with X. You can start with any leaving group here, right? But usually we start with X. What do we need for lithium? These are called alkyl lithiums. reaction to alkyl lithium. How to make RLI. What do we need? We need lithium, right? Of course, we need some dry ether, some dry solvent, right? Okay, so far so good. What charge is this guy on right now? This is negative, like chlorine bromine. This is positive when we start. How should it end up? Negative when we end, correct? How are we going to get there? Okay, so the first step may be this. Now, what do you know about lithium? Group 1. What does that mean? It has one electron in its outermost shell, correct? So if lithium is a great metal, what will it do with its one electron in the outermost shell, the valence electron?
Give it.
Give it away, right? So when it gives it away, what does it become? Lithium plus, right? Okay, so that's what we're going to do. We're going to write here, lithium, right, it's got that one electron, and give it away. So now we have Li plus. So they have it written in a curve. It's the same thing. All right, so let's see. They use methyl chloride. All right, so when I do this, I have one electron and I gave it away. Where did it go? Matter cannot be created or destroyed. That electron had to go somewhere. Where is it going to go? Well, it goes here. So I'm going to change this to methyl, exactly the same one, so you can follow it, okay? So instead of methyl RX, I'm going to use what? Methyl chloride. That's what methyl chloride looks like. So I'm telling you that I just gave away an electron, and it's hanging around. That electron is going to see this thing hanging around as well. So we're going to, somehow, it finds this thing, right? And so CH3, Cl, 1, 2, 3, 4, 5, 6, put in the brackets, put the electron out here. Because I'm not really sure where that electron is, but it's around this big thing. So in the book, they have the square and the brackets called a radical anion, right? This is a radical. Now the anion part, if you gain electrons, what charge do you get?
Negative.
Negative. So we're going to put that negative, here's the radical, and the negative right next to it, because we gained an electron. So in the book, they have called it radical anion. So what have we done? Alkyl halide. Lithium gave away its one electron. That electron found this thing somewhere living around this thing. We don't know exactly who's holding that electron, but we know it's around that thing. So we put everybody in brackets. We make this radical anion. All right, what's next? Well, this Cl would love to be Cl minus, right? That's usually what chlorine likes to do. It likes to become a negative. So here, how many electrons, when you do chloride, chlorine has 7. Group 7, 7 valence electrons. Chlorine is a nonmetal. It will gain an electron, right? So if you gain an electron, you will have 8 now, right? When you have 8, you gain an electron, so you gain a negative charge, true? So this is what chlorine wants in life, to become negative, okay? So here we have 6. You see these two? They're being shared. If I want, how many at the end? 2, 4, 6, 8. How many do I have here? 2, 4, 6. I can steal these 2, but it's so much easier to say, you know what? I don't want to steal anything from anybody. I'm going to take the one I brought in, and this new one that Lithium gave me, I'm going to hook up with that one. So do I have 8 now? I do. 6 here, 7 that I came is mine, 8 that I got from Lithium. Got that? So this is what happens. So we're going to end up with this. They have it written like this: minus Cl dot 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 dot, and then a negative charge. All they're saying is this chlorine is going to break off. Okay? So if the chlorine breaks off, what about the carbon holding these 3 hydrogens and 1 electron? What is that carbon now? It has 1 electron. What do we call things that have 1 electron? Remember we said hydrogen has 3 different ways to exist. Negative, positive, and what's the third way? What?
Oh.
Radical. So you see this one electron with carbon? It makes a carbon radical. So now we have CH3 with a radical, right? Because chlorine left, made a radical. Do you know anything about radicals in history? Free radical? Usually overthrow the government, those are free radicals, right? So they're kind of like heated, they have a lot of energy. So what do you think about this guy? Same thing. It will not exist very long. It's going to react right away. So this is a methyl radical. Now, remember the goal. The goal is to make RLi, right? That's my goal. Or methyl lithium. That's my goal. This is the goal. So keep your goal in mind. So if we have a radical here, do you remember when I did the lithium reactions, how many lithiums am I supposed to use? I used 1 magnesium, and how many lithiums I said? 2. Somebody caught it, right? So I have to introduce another lithium here. Now that lithium, a new lithium, not anything to do with the one before, that one's done. So there's a new lithium, second lithium. And this lithium is no different than this lithium. It wants to do the same thing, right? Good metals like to give away electrons, right? So the same thing that this one did, this one's going to want to do. It wants to become lithium plus. And when it does that, it has to give away that electron, right? So that electron is going to be given away to who? Well, do you see this? 1 electron means unstable. How many electrons in an orbital? 2. So when you see this is very unstable. Because you're supposed to have 2 in the orbital, not 1. Got it? So can somebody make this guy happy and make him stable? You gotta find an electron. How are you gonna find that electron? Who's gonna give you another electron? This guy. So when we hook up with this one, what are we gonna get? CH3 ... right? 2. So we're going to get this negative charge here. And what does negative always hook up with?
Positive.
Anybody positive here? Lithium. So this one is going to be attracted to this one. So we get CH3, Li. Or this. We're done. So this is the alkyl lithium. So what did this reaction entail? How many lithiums? 2. What did each lithium do? Donate 1 electron, correct? What was our starting material? Alkyl halide, something with a leading group, right? What happened? We grabbed the first electron. Nobody knows who's holding it, right? But we grabbed it, then chloride, Cl- decided to leave because it's stable with the 8 electrons, octet rule, right? Chlorine says, if I can get 8, I'm taking 8. Take the one that I brought in, that I'm sharing with carbon, and my other 6, and this new one that lithium just gave. So I'm 8, I'm good, I'm out of here. Cl-, stable. To the right, yeah, I'm fine. And then that leaves out radical, a very unstable thing. So who's going to make this unstable thing calm down?
Lithium.
The lithium, that's the second lithium. Comes in, gives an electron, makes methyl minus. Then what? Hooks up with plus minus alkyl lithium. So that's how we make our alkyl lithiums. The next thing we have to do, I guess tomorrow, is to do the Grignard. See how this step by step? Okay? Does it make sense to you how it happened? Okay? So now the Grignard tomorrow is even easier than this one. It only has 1 magnesium, 1 metal. Okay? So tomorrow's perfect.